In this lesson, we see a quick introduction to Maxwell's equations, that are equations that govern a topic that is usually called classical electrodynamics. So we see first what happens when we introduce time-varying sources to the field. Previously, we studied electrostatics, that is produced by electric charge, and we also studied magnetostatics, that is produced by stationary currents, so constant currents and constant charges. And we assume now that we have time-varying charges. And therefore, the equation of electrostatics, for instance, the divergence of D that equals the volume charge density, the curl of E that equals 0, and the relationship between D and E, when we are in the presence of time-varying charge densities, we have time-varying electric field and electrical induction. Similarly, the equation of magnetostatics that are summarized here in microscopic form, the divergence of B, the induction, magnetic induction, is 0. The curl of H, the magnetic field, equals the current density, J, and the relationship between B and H in free space, B equals mu naught times H, in the presence of time-varying currents, yields time-varying magnetic induction and magnetic field. There is, however, a link between the current and the charge that we already found. The current is the variation of charge, of flux of charge through a given surface, and if we consider a volume bounded by a closed surface S, the total flux of the current density out of the volume, that is, the total current exiting this volume, must necessarily be accompanied by a diminishing, a change over time of the charge density inside the volume, so that our current is produced by charge. This produces a link between electric phenomena governed by charge and magnetic phenomena governed by currents. So, what happens when we do a circulation of the electric field with the time-varying sources? We have, experimentally, that the circulation of the electric field, unlike the electrostatics that was 0, in this case produces a variation of the flux of B through a surface whose boundary is the line on which we do the circulation. The relationship between the flux and the circulation is, as usual, the right-hand rule. So that this circulation can be carried out over an imaginary line that we plot in space, and here, this circulation of E, unlike the electrostatic case, we observe a non-zero value. This is transferred similarly to microscopic level, in which the curl of E is no longer 0, but it's equal to minus the time derivative on the magnetic flux induction over time, the time derivative. Now, the circulation of the electric field over a closed line can be seen as electromotive force applied to this line. And in particularly, we are concerned on the case in which, instead of an imaginary line that we plot in space, we have a wire on which there can be a current flowing, and let's suppose that we are in the presence of a flux of B that varies over time. This equation, Faraday's law, tells us that there is an electromotive force, a voltage difference, we can say, in this wire that produces a flow of current due to the time variation of the flux of B on the surface. Now, the effect of this current is to produce another B field that opposes to the flux variation of B, so that, as you see, we have a flux variation, delta B, which is oriented like in this picture. We have a current produced by delta B as an effect of the electromotive force, and we have another B field produced by I, the current, that opposes to this flux variation. Another very important phenomena is that represented by Ampere-Maxwell law, another relationship between electric and magnetic phenomena. On one side, we have the circulation of H over a closed line that we can plot in space. We know from electrostatics, from magnetostatics, that this circulation of H must equal the total current crossing this, the surface whose boundary is that line. So that should be equal to this white term. But Maxwell discovered that there is a missing term in this when we are in the presence of time-varying phenomena. The missing term is actually the flux of D, the time derivative of the flux of D through the surface whose boundary is the line on which we carry out the circulation of H. So we have, as you see, several quantities. We have H, which is plotted in white here. We have J, that can be somewhere in space. We have D, and in particular the flux of D through this line. J is the green arrow, and D is the orange arrow. At the microscopic level, this means that the curl of H is no longer equal to J, which is Ampere's law, but rather, Ampere-Maxwell's law, the curl of H equals J, the current density, plus a term that is the time derivative of the electrical induction. Why this term? If we consider, for instance, the very simple circuit that is composed of a time-varying voltage source and a capacitor on this side, there's a current that flows thanks to the fact that there are time-varying phenomena, so that on the capacitor we know that there will be some current flowing in this circuit. We know from, for instance, from circuit theory. Okay, so let's consider a closed surface that embraces on this left side the wire, on the right side the inner part of the capacitor. Now, the circulation of H is carried out on this yellow line. Clearly, these two surfaces, S1 and S2, this is the splitting due to this line circulation on which we carry out the circulation of H, should provide the same value for the right-hand term, because on the left-hand term we have the same circulation of C. Unique value for the circulation must equal to the same right-hand term on this equation, because these two surfaces, S1 and S2, have a common boundary, which is the line on which we carry out the circulation. Now, on the left part, it is quite clear that the circulation of H produces I, because it's the flux of I. On the right surface, S2, there's no I, because here in the capacitor, there's no current I. So what is the right-hand term contribution that equals the left-hand contribution, which is the circulation of H? Is the flux of D. We know that in the capacitor, there is a D field, there is an E field, and this time-varying flux corresponds to a current. We can call this current displacement current. So that the well-known equation that gives the current in terms of the time derivative of the voltage through the multiplying term, which is the capacitance of the capacitor, can be translated in the form, can be obtained as a result of Ampere-Maxwell law. So we are now able to write down the complete set of Maxwell's equations, both in differential form and in integral form. Now, in differential form, we have that the curl of E is no longer zero, but it's rather the time derivative of the magnetic induction. And the curl of H equals the current density plus the time derivative of the electrical induction. In addition to this, we have the same equation as in the static case for the divergence of the two fields. The divergence of D still equals the volume charge density, and the divergence of B still equals zero. This microscopic form or differential form of Maxwell's equation are easily translated or derived from the integral form, in which, when we see the curl, we write down the circulation, and on the right-hand side, we write the flux of the corresponding quantity. So that these two correspond to the Faraday's law, and these two correspond to Ampere-Maxwell's law. Again, we have that for a given closed surface, the total flux of D must equal the charge inside this volume. And also, for a closed surface, the total flux of B, the magnetic induction, must equal zero. An immediate derivation from this equation is the continuity of charge and currents that states that a given flux of current through a closed surface must correspond to a change, to a diminishing of the charge, the total charge inside the volume whose boundary is that surface. So we have a minus time derivative of the total charge inside the volume. In microscopic form, this can be translated thanks to the divergence theorem to divergence of J equals minus the time derivative of the volume charge density. Okay, now in vacuum, there is a proportionality relationship between D and E and between B and H, so that we can write Maxwell's equation now for instance, only the E field and the H field. This system of equation is now solvable because there are a number of equations and a number of unknowns that make these two compatible for the solution. Because previously, if we do not introduce a constitutive relationship between B and H, between D and E, Maxwell's equations are not solvable. There are too many unknowns. So that we can write, as we did before, the same set of equations in which we only have the presence of E and H. And this is just what we obtain both in differential form and in integral form. If we look at specific variation over time, which is the sinusoidal variation over time, this is a very important domain because in sinusoidal domain, when we are in presence of linear relationship between various quantities, a sinusoidal source produces a sinusoidal field at the same frequency. And an important aspect of this sinusoidal frequency domain is that the time derivative of a sinusoidal function, it can be written as the algebraic operator j omega that multiplies the same function, so that we get rid of time derivative in Maxwell's equations. So whenever we see a time derivative, we just write j omega because we assume that a dependency, of a sinusoidal dependency exponential j omega t is present everywhere and is discarded from these equations. This means that E and H are now complex functions of position that represents vector phasors and in which there is no longer a time dependency. There is a space dependency, but there is not a time dependency because we know that the time dependency is sinusoidal at frequency, angular frequency omega. As you see, we get rid of all time derivative and we are left only with space derivative. The set of equations is rewritten here for clarity. And also for the continuity between charges and current, we obtain the same result. Whenever we see a time derivative, we replace it with the algebraic operator j omega multiplying. When we are in presence of materials, this is a very important aspect of Maxwell's equation and a very complex aspect of Maxwell's equation, the interaction of electrodynamics with materials, electrodynamic field with materials. In general, we can simplify for the purposes of this course this relationship in the form of a scalar multiplying term between D and E as we did in electrostatic and between B and H as we did in magnetostatic. So that for us, we can assume that the permittivity and the permeability are constant. They can be maybe function of position, but constant. If we are in the presence of what is called time dispersion, so that the response in the time domain is non-local, this can be easily represented by epsilon and mu, which are functions of omega. But for a given omega, they still can be written in the form of a proportionality between D and H, between D and E, between B and H. So that whenever we see in Maxwell's equation from the previous slide, mu naught, epsilon naught, now we can replace this with mu and epsilon that account for the presence of a material with different parameters. And the result are this set of equations both in, as you see, differential form and integral form. As we did with electrostatics, these fields, when you are in presence of different materials, must obey some specific boundary conditions. And we could show that the boundary conditions are perfectly equivalent with what we already studied in the electrostatic and magnetostatic case. Specifically, we have that the tangential component of the electric field must be continuous in the passing from one material to another, and so must be the tangential component of magnetic field when there is no electric surface current flowing at the interface. If there is an electric surface current flowing at the interface between the two materials, the boundary condition for magnetic field is represented by this equation. Similarly, the normal component of magnetic induction must be continuous between two materials, and the normal component of electrical induction must be discontinuous only if there is a surface charge density at the interface. This set of 4 equations are perfectly equivalent to the equation that we already studied in magnetostatics and electrostatics.